After discussing the different navigation patterns, we can now move to complex state management. As we know, widgets in Flutter are organized in a tree structure. This means that each parent widget knows its children, but the children are not aware of their parent. In addition, siblings widgets cannot communicate directly, since they must interact through their common parent. If we only have a single state element to manage, things remain simple. We have already seen this when introducing stateful widgets, where the state is maintained inside the state manager, and the code can be organized in different ways. This simpler approach is usually preferable whenever it is sufficient. However, when we have multiple state elements on the same screen, different situations may arise and they must be handled properly. If the state elements are independent, then the solution is straightforward. We simply duplicate the stateful widgets. Instead of having a single state element, we might have several of them, but this does not introduce additional complexity. On the other hand, if different state elements must be synchronized or shared, we need to adopt a specific approach. In these cases, we introduce a dedicated pattern for managing shared data, usually referred to as state hoisting. To recall the key ideas, let us consider a very simple app where we have a button or a switch controlling a light bulb. Whenever we toggle the switch, we want the bulb to turn on or off. If we keep toggling it, then the state alternates between on and off. The code for this example is quite standard. We use a simple stateful widget that implements the controller of the bulb, which in this case is called bulbctrl. The structure of the application is the usual one, so there's no need to comment on it in detail. We define the main function, which calls runup, and then we create the typical structure based on material app and scaffold. If we look at the main widget of the application, we see that the stateful widget is responsible for managing the state of the bulb and updating the user interface accordingly. If we consider bulbctrl, the structure is quite simple. The stateful widget itself is straightforward, since it only needs to overwrite the createState method. Bulbctrl state, however, is slightly more interesting. In this case, to switch the bulb on and off, a simple Boolean variable called active is enough. We then define the method handleClick, where we simply toggle the state of the bulb. This is done inside setState to ensure that the graphical user interface is rebuilt. The most interesting part of the code appears in the build method. Besides creating a center column, we use the well-known ternary operator column to decide which icon should be displayed. Depending on the value of active, we show either a filled light bulb icon or the outlined one. We also use the same condition to choose the color, yellow when the bulb is on and gray when it's off, just to display the outline. Finally, we define the button that controls the switch. This is an elevated button where the onPress parameter is set to the handleClick method, and the child simply contains the text push. Now, if we want to build something a bit more complex, we need to consider a slightly different situation. In fact, we can have two possible cases. The first one is simply duplicating the bulb and the switch. Instead of having only two elements in a column, we could have 4 elements, or we could create a column containing 2 bulbctrl widgets. In this scenario, each switch controls its own bulb, and the 2 bulbs can be turned on or off independently. Let us now consider a more interesting case, where the 2 bulbs must be synchronized. In this situation, we cannot have both bulbs on or both bulbs off at the same time. When the user presses a switch to change the state of one bulb, the other bulb automatically changes its state as well, even if its switch was not pressed. In other words, the system must always keep exactly one bulb on and the other one off. This situation creates a problem. In this case, we have two bulb CTRL components, which would normally be implemented as two stateful widgets, each with its own state element. However, the two elements, called bulb1 and bulb2, are children of the same parent widget. The red arrows in the diagram represent information flows that are not normally allowed in the standard object-oriented structure. The parent widget, besides creating the two bulbs, can clearly communicate with them. If the parent has references to its children, it can call methods or pass data to them. However, the red arrows represent interactions that are not directly supported. As already mentioned, bulb1 and bulb2 cannot communicate directly with each other unless we introduce special purpose code. Furthermore, the two bulbs are not aware of the parent that created them. They simply exist in the widget tree, but they do not know who instantiated them. For this reason, a child widget cannot directly call methods on its parent. To solve the problem described earlier, we must apply the concept known as state hoisting. State hoisting is important because it suggests that instead of distributing the state across the children, for example, one state variable for bulb1 and another for bulb2, we move the state and its controller to the parent widget. In this way, the parent becomes responsible for managing the state of all its children. As a result, the parent becomes the central or smart part of the system, while the two children can remain stateless widgets. Their role is simply to display the information received from the parent and notify the parent when an interaction occurs, for example, when the user presses a switch. To allow the children to communicate with the parent, we usually adopt special callback methods. The parent provides references to these methods and passes them to the children as parameters. The children can then call these methods whenever they need to notify the parent about an event or an interaction. In a simple way, this can be compared to giving the children a phone number to call. The parent gives this number to the children, and they can use it whenever they need to communicate. The children do not really know who owns the number or how the communication is handled internally, but they know that by calling that number, they can interact with the parent. In Flutter, this mechanism is commonly implemented by passing callback functions from the parent widget to its children. When a user interaction occurs, such as pressing a button, the child calls the callback, and the parent can update the shared state accordingly. In Flutter, these special purpose callbacks are usually represented by a specific generic type called valueChangedT. This is a generic function type that represents a callback receiving a value of type t as its parameter. In other words, valueChangedT is used to define a reference to a function that is called whenever a value changes and that receives a value of type t. If the callback function does not return any value, we can use another special function type called voidCallback. This represents a function that takes no parameters and returns void. In other words, it's simply a reference to a function that is executed when an event occurs. These two types, valueChangedT and voidCallback, are commonly used when we want to provide the children with references to methods defined in the parent. When the child calls one of these callbacks, it is effectively communicating with the parent widget. In this way, the child widgets do not need to know anything about the internal implementation of the parent. They simply call the provided callback, and the parent can then update its state or perform the required action. This lecture has introduced the main concepts behind complex state management. Now we can understand how to make it work.